Hi, my name is Puteri Dayini, Binti Mohammad Sukri.
Hi, my name is Puteri Damia Adlina, Binti Hisyamuddin.
Hi, my name is Ahmad Shazili Shaharin, and this is our MAT183 group, and this is our video presentation on application of differentiation, applied maximum and minimum.
Imagine designing a box with the goal of using the least amount of material while still maximizing the interior capacity. This is a perfect example where differentiation comes into play, guiding us to the most efficient solution. But how do we approach this mathematically? Calculus helps us solve this kind of problems by using differentiation. It shows how a function changes and helps us find maximum or minimum values, like maximizing profit or minimizing cost. It is an essential tool for solving optimization problems and making the best decisions within given constraints. Now that we understand how it works, let us explore its real-world applications. The first problem, imagine you are designing a rectangular garden where one side is a rock wall and the other three sides are enclosed by wire fencing. You have 40 meters of wire available. How do we find the dimension that maximize the area of the garden? Let us break it down step by step. First, we want to maximize the area, so our objective function is A equals to S times Y. And since the fencing forms the perimeter of the other three sides, so our constraint is 2S plus Y equals to 40. We rearrange to solve for Y, giving us Y equals to 40 minus 2S. Next, we substitute Y equals to 40 minus 2S into the area formula. When we expand, it becomes A equals to 40S minus 2S squared. To find the maximum, we differentiate A equals to 40S minus 2S squared with respect to S, and we get 40 minus 4S. We set this equals to 0. Solving for S, we get S equals to 10. Now we check if S equals to 10 gives us the maximum using the second derivative test. The second derivative is negative 4, and since negative 4 is less than 0, the function is concave downward, confirming that S equals to 10 is the maximum. Finally, we find the maximum area by substituting S equals to 10 into our area formula. So A equals to 40 times 10 minus 2 times 10 squared. That's 400 minus 200, so the maximum area is 200 square meters.
Introduction. To solve this problem, we start by creating a constraint equation that represents the relationship between the variables. Step 1. Create constraint equation. Let's consider the equation is 5x plus 2y equal to 200. This equation represents the sum of 5 times the value of x and 2 times the value of y, which equals 200. We can arrange the equation to isolate y by divide 2. So, y equal to 100 minus 5 over 2x. Step 2. To find the maximum area of the rectangle under the given constraint, we need to create an objective function and substitute the constraint equation into it. The area of the rectangle is sy. Substitute constraint equation. From the constraint equation, y equal to 100 minus 5 over 2x. Substitute y in the area formula. So, area equal to s multiplied by 100 minus 5 over 2s. So, simplify the equation, you get the area equal to 100s minus 5 over 2s squared. Step 3. To find the value of s that maximizes the area, we need to take the derivative of the area function, set it to 0, and solve for s. First, derivative of the area function, dA over dx equal to 100 minus 5s. The second one is set the derivative equal to 0. dA over dx equal to 0, so 0 equal to 100 minus 5s. And the last one is solve for s. So the answer is s equal to 20. Step 4. Do the second derivative test. To confirm that s equal to 20 is indeed a maximum value, we need to perform the second derivative test. d squared a over dx squared minus negative 5. Since the second derivative is negative, it is confirmed that s equal to 20 is the maximum value. Step 5. Calculate the maximum area. To find the maximum area, we substitute x equal 20 back into our area equation. Area equal 100 multiply 20 minus 5 over 2 multiply 20 square. So, you get the maximum area equal to 1000 meter square.
So for problem 3, we're going to use the optimization method to maximize the total profit. So the problem statement, find the maximum profit for the company given the revenue function Rx equals to 2000x minus 10x squared and the cost function Cx equals to 2000 plus 500x, x equals to number of items. So note that profit equals to revenue minus cost. The first step is we're going to create the profit function. So by using the formula profit equals to revenue minus cost, we get that Px equals to 2000x minus 10x squared minus 2000 plus 500x. So the profit function will be negative 10x squared plus 1500x minus 2000. So the next step is we're going to find the derivative for the profit function. So we're going to get that dp over dx equals to negative 20x plus 1500. So the third step is we're going to take the derivative and equal it to 0. So negative 20x plus 1500 equals to 0, and we're going to get x is equals to 75. So the fourth step is we're going to do the second derivative test. So we're going to get d squared p over dx squared equals to negative 20. So we get that x equals to 75 is maximum value. So the last step is we're going to calculate the maximum profit. So we're going to plug in the value 75 into our profit function. Negative 10 times 75 squared plus 1500 times 75 minus 2000. So by substituting the value into the profit function, we can conclude that the maximum profit is 54,250. In conclusion, we can use differentiation method in mathematics and various applied fields. By using derivative, we can identify the best approach on optimizing with the area of a field or profit and loss. This proves that derivative is essential for solving real-world problems in economics, engineering and science, where optimizing area, cost and efficiency is crucial. So that's all from us. Thank you.